Welcome back, everybody. And I wanted to give you just a quick overview of the plans for today. So thanks for coming a little bit earlier. I was thinking that we could have this as a kind of workshop-like thing. But what I also wanted to do is to cover this topic about recurrent neural networks, because that links very well with the solution of differential equations. So that if for those of you who have chosen that path, this is something which we can easily tie and attach to that. And again, if you think of the project, there is also the possibility to define your own path. If you wish to write a recurrent neural network code, that's also a possibility. And I know that Greg here has been writing a convolution neural network code.
Basically an interface.
Yeah.
A bit like TensorFlow, that's what I went for. So I think by the end you can build both STMN and RMN with it, maybe more.
So the thing I just wanted quickly to remind you about is the topic which dealt with the convolution neural network, which we more or less wrapped up last time. And there is an example in the slides. So I actually merged the slides from last week and this week. And you have the link in the, I sent the link to you, but you also have it in the so-called weekly schedule of the university. So I don't know how much you have been looking at that official website of the university. So normally people never look at it, but there is an official website, and I tend to put all the information there. So if we just switch a little bit here, just to quickly remind you of that. So I normally put under the schedule, you will find the teaching material and also the videos of the lectures. So like here, you will find the lecture notes, which I'm going through today. And I do always this mix of a whiteboard and slides. You will also find the messages, and you also gotten the emails, right? So if you don't get the weekly email, just let me know. Okay, so that was just a little bit about practicalities. So what we did till last time was actually to look at how to set up a convolution neural network. And that normally consists of a convolution part where you do the mathematical operation of the convolution or the filtering. And then this result, which is normally a reduced image or a set of reduced images, because the filtering is often done in many stages. So you can have many convolution parts. And that information is then fed, this reduced image or reduced images are then sent to this, function which modulates the results. Normally it's given by a rectified linear unit. And this is a function which has no parameters normally. And it's a function which is fixed by you at the beginning of the calculations. So that belongs to the architecture of the network. And then there is a so-called pooling layer where the standard technique is a max pooling, where you take adjacent numbers or in nodes, and you look at the result which has the maximum value, and that's the one you propagate. So if you would looking at 4 adjacent nodes, and you would then pick the one which has the largest value, so you would typically reduce from 4 to 1. But when you run the pooling, you have parameters by which you can set how many adjacent nodes you want to compare. And max pooling is normally the one which is preferred or is mostly used. And then you have when you've done the systematic reduction, you will typically send this into a standard feed-forward neural network with additional training parameters. And you would train everything with a backpropagation algorithm. So that's the backbone of everything which we deal with. So this example here, I'm not going to run it again because I ran it last time, but I just wanted to quickly remind you that I would normally recommend, if you are not too familiar with things, to run it with an API like Keras, which interfaces TensorFlow. That's the one which will save you time and make you productive in the short term. Then clearly you can think of using TensorFlow and program in TensorFlow. it's the same as if you were to use PyTorch, or alternatively, if you want to have this computational path where you write your own code. That's also another possibility. For the differential equations, people have actually been started to use convolutional neural networks in order to reduce dimensionalities where you filter. So your filtering is actually dimensionality reduction. But the most, or I would say the most straightforward way to move from a standard feed-forward neural network to the kind of dynamical equations we're looking at is a recurrent neural network. And that's really tailored to time series and sequences of data. It has been widely used to, let's say, language processing. We will not touch upon that at all. So I have basically no interest in it. It's just an honest statement. I'm more interested in the solution of differential equations. And yeah.
Do you think the transformer model, which obviously both Google and Meta and OpenAI have been known for in the last couple of years, could be used to solve partial differential equations too? Because it has the ability to take larger inputs than recurrent neural networks.
Exactly. That's an interesting point. That's
I was like wondering about it.
Yeah. So in the projects, and this is something I wanted also to discuss with you guys, how we're going to finalize everything with the exam, because we are going to run an oral examination. But what I would like to propose is that we simply work on one main project, and you can split this up in minor parts if you want to, and that counts something like 70% of the grade. And then we have a final oral examination, which only counts 30%, where you basically what you do is to present your project. So that would mean that you present it, and it takes, like, say, 30 minutes, 25, 30 minutes. And then there will be questions, something like 10, 15 minutes, and then we're done. So that is one way of actually wrapping up what we have done here. And okay. We can just, just take the table, bring the table closer, or you can get closer here at the end. So the thing which you're going to see now when we bring up this example with recurrent neural networks is that the setup is very similar. So the setup here is you define a sequential model. In this case, you have a convolutional layer, and then you have the max pooling stage. You flatten out the results, and then that is fed into a dense layer. We'll have a given number of neurons. You define the type of filters you want to have. And then at the end, you have an output layer, where in this case, since we are dealing with a classification of 10 handwritten numbers from 0 to 9, we have a so-called softmax function as the function which modulates the data, or normally what we call an activation function. And you specify the type of optimizer you want to use. You can do standard stochastic gradient descent. You can do an ADAM, RMS prop. So these are all options which are baked in here. And then you specify the number of epochs, the batch sizes, and all these kind of standard parameters which you would specify when you're setting up the network. You specify the number of fields. If you have no padding, input, then it uses the default value, which is 0. The default value for the stride is 1. So if you don't specify anything, these will be the default values for the filters, at least as far as I remember. And this is just a interface which I wrote, and it runs over the learning rates and the hyperparameters, and then it simply evaluates the score, which in this case here is just the accuracy of the reproduction. So you just simply count the number of times you predict properly and divide with the total number of cases you have. And then there is a way to visualize it. So I'm not going, I'm not going to run that one. But I wanted to give you now the kind of examples which we are going to encounter. And then I'm going to switch over to the whiteboard. And I'm going to link this very much to the solution or the differential equations which we have. And after this, we are going to discuss autoencoders and general adversarial networks. And that will terminate basically the kind of lecturing part. So that means that after the break, the Easter break, we are going basically to just deal with project work, if that is okay. Unless you miss me so strongly that you want me to lecture all the time. Okay, so this is again a simple recurrent neural network. And in this case, I have a support function here, which converts my data into a matrix, but the data is now given by a sine function. And you can think of this, so what I want here is to use this sine function as a way to predict what will happen later. So I'm going to use 1,000 time steps, but I'm going to use as training the first 800. So my recurrent neural network will be trained on the 800 first points. And after that, what I get from the network is a prediction. So you could think of you splitting the data into 80% training and 20% test, where test will then be data which it hasn't seen. Now, this is a periodic function, so this is very easy. It's not a very exciting one, so it should do pretty well in training. And if I take away this noise, so let's take that one away first, and then we just run it. So I just define a simple recurrent neural network, which has 32 units. And I'm coming back to what this means in the detailing of the calculations of a recurrent neural network. I have a ReLU activation function, and I'm going to have inside that one, I'm going to have every node then, as we are going to call them at the time step, is going to be given by a dense neural network. The loss function is a mean squared error because I'm fitting a function. And I'm also having an optimizer, which is the root mean square propagation. So this is basically the network which I'm setting up, and then I'm training, and then I'm making a test prediction, and then I just concatenate the results, and then I make a plot of everything. So if we now run this, it's just going to take a little bit time here. So take some time. Another option, which is a thing which I normally recommend to set up, is the model summary, which tells you how many parameters you have to fit. So this is not a very large case. And you see that the total trainable parameters, which are the weights and the biases of the recurrent neural network, they are roughly 1,500. So I'm running through the number of epochs, and then at the end, I should be able to make a prediction. So let me just scroll down here a little bit. It takes a little bit more time, as you see, and you will see that these kind of recurrent neural networks are really CPU intensive. So what I've done here now is to fit to 0.800. So the blue line which you have here is the original curve, and the orange line is actually the prediction which I make. So my sine function, this is not a very exciting function. It's a very easy function it's a harmonic function. It repeats itself with time. It sounds almost like me, just repeating myself. And it's not very exciting either. So if we add some noise, you will see that it starts failing. And you will see that if you go back here. So you can see in this specific case, this recurrent neural network, you have a periodic function. They do extremely well. So if you have differential equations with periodic solutions, a recurrent neural network is a fantastic way to fit to just some few data points, and you can easily make a prediction without solving the equations. And that's extremely powerful. But clearly, if you add some noise here, then you will see that then the results are not going to be that good anymore. So in this case, if you look at the loss function which you have, you typically have 10 to the minus 4. And I'm going to explain to you how you calculate the loss function as well in this standard way. So there are some technicalities which I wanted to go through actually. So if you rerun it now with this, you're going to see that the loss function here, this is the accuracy, which in your case is the root mean square error, is not getting much smaller than 0.3. And this is simply because we have lots of noise here. But this tells you simply how, actually this example here is an example you could easily use on the differential equation, which you first solve with a standard feed-forward neural network. Because the inputs and the outputs, as we're going to define them, are going to be very similar to what you have with a feed-forward neural network, except that we're going to interpret them slightly differently. So you see now that, so the orange one is my behavior of, so this is what the model gives. So the blue one is my original data with noise. And you see now that it follows the periodic behavior, but it doesn't do a good job here. But this is expected because I have a pretty large noise. So you get the periodic behavior roughly, but the exact reproduction of the data is not impressive. So what I want to do now is more to switch a little bit over to the whiteboard. And most of the material is also included in the slides, but I find it often better to actually go through the notes here with the whiteboard. So let me just change, and then we are going back to the slides a little bit later. So we have a, so let me just write this one, and then it's the big day in March. Happy March 8th to all of you. So the topic now is just the RNNs. And the best way to actually look at this is often with a graphical representation. So before we begin, I just wanted to give you a kind of a brief introduction to the graphical representation, which is widely used when you're thinking of many of this type of networks. And then it's easier to understand what's going on when you look at a graph. So typically what you will have then is a notation where, suppose now you have a result Z, which is X times Y. So this would, in a graph, as a graph, it would be written like this. So you would have some input X, and then you have an input Y, and then you would indicate what kind of mathematical operation you're doing. So you would often see something like a multiplication sign or an addition sign or whatever. So this is a typical graph. If you go back to what we did with the neural networks and you look at the input to an activation function, so you would typically have something like a Y where you have a function F, and then you had the input data X, you have the weights, which is a matrix, plus a bias, something like this, and this is equal to F as a function of a quantity Z, where Z is now the argument to that function F. And this function F could be a sigmoid, it could be a ReLO, or any of the activation functions. And the typical way you would draw this would be something like this. So here you would have X transpose, this is a vector, and then you feed in X here, you feed in the weight matrix, and you would typically do a matrix multiplication or dot product, depending on what you're interested in. And this now feeds in to the function. So we are feeding that into an F of Z, and this gets an input B here, and we have an addition here, and then this results in a final value Y here. So this would be a typical situation which you encounter. And this function F could be a ReLO function. Then you would typically indicate if Y is, suppose now that Y is given by the standard ReLO function, that's given by a max of 0, and then you have the argument Z, and this is now your F of Z, and then you would simply indicate that this is now given by the ReLO function. So it's common to indicate what kind of mathematical operation you're doing, or you just leave it unspecified. So if you now have a kind of dynamical system which evolves over time, What you would see then is something like, suppose you have a system which is driven by an external signal. Driven by an external signal. Suppose this external signal is just x at a time t. Then what you would have then would be some kind of function s of t. And this is pretty general right now. We haven't specified what s of t is, but it's the state of the system at a time t. And that is normally given in terms of the state at the time t minus 1. You may have an input x of t into the system at a given time. And then you have a set of parameter theta, which you then need to specify. So these parameters could be given, or you would have to define them by an optimization process, like what you would do in a recurrent neural network. So the typical way you would write this is one, in a very rough way, as a kind of a compact way. So you have an x which feeds into s, and then there is some kind of loop, and then there is a black box here, which is then represented by this function f. This is something which you would open up. So when you unfold it, it means that you would have some s at a given time, an ancient time. It could be the initial time you have. And this one feeds into the function f. There is an input x at a time 1. Or let's just write it at a time t. So we assume now that we have done this many time steps. This produces an output. And we may not be interested in observing that output. Or we could observe it when we're coming back to that. And then we have a new function here. And that gets a new input, which is an x of t plus 1. It produces a new output. So let me just write it like this. And then we have an s of t plus 1. And this continues all the way till the final time, or the final stage. We don't need to think of this as time. You can think of this as a final stage. So I tend to think in terms of time because I'm often interested in dynamics. So the type of problem which you then have is, how do you actually define these functions f? And one way to look at this is now to go back to the project and look at one of the differential equations which we have. So a recurrent neural networks, they are normally tailored to studies of such sequences. And this is their strength. And they are specialized for time sequences and processing a sequence of values. This is really where, if you have data sets like that, this is really what you need to think of. And RNN is really ideal for that case. And you can think of at each stage in this recurrent neural network as a kind of specific time step or a specific stage in the calculations or the analysis of the data. And typically an RNN, when we are now setting it up here, it contains the following. RNNs contain, you would typically have at each stage. So think of stage as time. There will be some new input. So that could be the s of t minus 1 and this x of t. So that's the input to a given stage. Then you manipulate the stage. Manipulate the state which you have. So this input defines a new state, and you manipulate that state via this function f. That's the one which modulates your results or your inputs. It's normally it reuses weights. And we're going to see that basically two different strategies. And the most common one is actually to reuse the weights in a network from one stage to another one. Alternatively, you can keep in memory the values of the weights and the biases for every single stage. And that clearly, if you have a deep and long time sequence, this is going to require a lot of memory, because you're going often to have more than just one hidden layer in the neural network, which is you have in every stage. And then it produces a new output. And let's see, let's take this one down because that's a little bit irritating. Okay. So at every stage, we produce a new output. And you can think of this as a series of measurements which we are doing. So let's now try to expand this simple model which we put up here. Because in this specific case, when you look at it, we didn't produce an explicit output which is visible to us. So what you could think of here is actually to have this S of t, if that is a specific output. This could be a number which the network now outputs at every time step. And this could be compared with a measurement you have done. In our case, that would be the solution of the differential equation, or like this sine function, which you saw in the slides. That sine function is the function we want to reproduce at every stage. And then the network itself produces an output at every time step, which is then compared with the final result. So let's now go back to the project. Project 1. Because that would be the next stage, and RNNs. Yeah, we actually thought of doing that because just take a chair here, right? So this will be on the recording anyway. I hope you don't mind. Yeah. You can get closer here, or you can. So what we've been doing is actually going through the recurrent neural networks. And what I wanted to is actually to link what we are doing now with the project here. And the one of the exercises, or one of the topics which we had, was this differential equation. So I'm just taking the simpler one, because this is something which is very easy to link with the buildup of a recurrent neural network. So you've probably seen this equation ad nauseam in different physics courses. So it's a velocity-dependent term. This is just a harmonic oscillator with damping, and then with an external force which is applied. And this depends on time, and this depends also on time. So typically what you would do now is, as we discussed earlier, you would define some initial conditions which start the solver. And then you would have an initial velocity because you have a second derivative. So that means you need two initial conditions in order to be able to solve the equations. And what you would do is to rewrite this as two coupled differential equations. And that is what makes the comparison with the Lorentz attractor. So in that case, we had three coupled differential equations, whereas here we just have two coupled differential equations. So that means that you have one for the velocity, which is simply dx dt. And then we have a coupled equation for the acceleration, which is a, which is dv dt, which again is d. Just to quickly remind you that, I hope you don't get offended if I remind you about the material you may have seen already kindergarten. And this is, if you just take that equation, you can rewrite this as this parameter eta divided by m, and then you had a velocity, because this first term here is just a velocity. So I just rewrite it like that. And then you have a minus x divided by m, and then plus this force. So that's a differential equation which we end up with. And the first order differential equation is this one, which we want. So if we now look at the typical way we can solve this. So in the project, I give you a Runge-Kutta solver, which is normally better. But here we can just limit ourselves to a standard Euler method. So this is now going to be given by x of t of I. This is a discretization we are making. And then we have v going over to v of I, which is v of t of I. It means also that x of I plus 1 is actually x of t of I plus some time step delta t. and we have a time, which is also discretized, and I'm using the same symbols, except that they have subscripts, and that's given by a time t0, initial time plus I times delta t, and this I runs from 0, 1, 2, up to n. And this delta t, just to quickly remind you of that, is the final time minus the initial time divided by delta t. Okay? So you've probably seen this kind of solutions before. And the simplest one is Euler's method, which is just a manipulation of a Taylor expansion, and where you keep terms up to the first derivative. So that would simply be given by x of I plus delta t times v of I. And then I have my v of I plus 1, which is v of I plus delta t. But now I'm going to change this a little bit. I'm simply going to rewrite this in terms of a function, f of I, where f of I now is going to be given, if you now look at the terms you have here, is going to be given by these terms here. So f of I is going to be some kind of function, which we don't need to specify. But this function f depends on f of I, it depends on x of I, and it depends on v of I. And time is implicitly hidden in f, x, and v. So I have suppressed the time dependence here. But you could say that the time dependence is actually given by this variable I. This is where you have your time dependence. But I don't give you a t of I here, because the solutions are given at the time t of I. So if you now look at this, and we go back to the way we represented the network, or this kind of graphical representation. So if you now look at this type of graphical representation we did, if you now think of this function which we had here, this s of t, this looks very much like what we had for the solution of what we have for the solution differential equation. So this s of t could now be the velocity at the time t, which then depends of the velocity at a time t minus 1. It depends on the position x at the time t, but it also depended on this force F. So you could think of this function F as now being something which represents this function which we see here, which has an explicit mathematical representation. So it means that when you now set up a network here, or you want to make a graphical representation of this, so if we do that, what you would have some initial condition v0, and that feeds in to this function f of 1. But what you also need to feed in here is f of I and x of I, actually f of 1 and x of 1. And then this produces an output, which is v1. And that is now fed into this new function f of 2, which then also gets a new input f2, x2 here. And that continues to the final time. And then just continues, and then you end up with a v of n minus 1, which feeds into f of n. And that produces that takes an f of n and an x of n, and it outputs a v of n. So that's my final velocity. And you could have a similar graph for the position. Now, the way you could think of this is in a slightly different way as well. So you could now think of you actually having a differential equation solver and experimental observations of the velocity. So think of you now running an experiment here where we now modify this graph so that at every time step, we output the velocity of the model. And then we compare that to an experimental observation. So we are going to modify this graph and make it closer to the way our recurrent neural network is going to look like. Except that then, when we have a recurrent neural network, these functions f's are going to be replaced by the hidden layers of a neural network. So that's going to be the distinction here. So that means that you, instead of you having a differential equation solver, you're now going to replace that with a neural network. So let's assume now that we have some observations. So we would start with a V0, the initial condition, that feeds in, so it's the same graph again. It feeds into this F1, which now receives, there's an external force, and you have a position X1. So these are parameters which you fix. And now it produces an output, which is this V1. But this output is also used in the next time step. So you get a F2 here, and that has a force here, which is F2 of X2. That produces a new output, V2. And then this just continues till we have the final. I'm just going to put in a little bit more space here. So that ends in the final, where we have my F of N, and that gets a input Fn xn. It outputs the final velocity of the system, but it also compares this with an observation. And now I'm going to plug in here. I need to squeeze in a little bit. So this is now fed into a function, which I'm going to call the loss function or cost function. So there's a function L1, and here we have a function L2, and this just continues with L3, etc., etc. And in here, I plug in my V1 observed. And in here, I plug in my V2 observed. So suppose you make a measurement of an object which is falling or which is moving in such a field, and then you're comparing that observation with your differential equation solver. And that is a way to just gauge the quality of your differential equation solver compared with experiment. You know the value of the force which acts on the object, you know the position it had, and then you simply solve the differential equation and compare your solution with an actual observation. So at the end, what you're doing now is that this L1, for instance, could be the absolute value, the difference between the observation and what the model produces, or it could simply be a root mean square error. So it's up to you to decide the way you gauge the quality of the data. The standard way of doing that is to take the root mean squared error. So it means that you would now have a loss function here of Ln, and this now receives also as input the Vn observed. And then at the end, you would have a total loss function or cost function, which is simply the sum of I equal 1 up to n of all these Li's. So that's the final cost function. And when we're going to take the derivatives and use the back propagation algorithm, we're actually going to take the derivatives of all these loss functions. So this is the total error which you have. Any questions so far? Sounds okay? So the thing which we can do next is actually to replace this function f with a neural network or hidden layers of a neural network. And these hidden layers can be one or many layers. They can be convolutional neural networks. They can be feed-forward neural networks. So you can actually, at every time step, you can actually make these as deep as you want. So if you're doing imaging and you have a time sequence of images, this could actually be a convolutional neural network which you have in here. But we're going to write this now when we go over to the RNN part. The way we're going to set it up is that we have a new function h. So we have this f is now going to be given by an h. So I'm going to skip that one. And this h of t is now going to be a function which now depends on, so this is the the v which I have, not this v of t is now going to be given by this h of t, and that has a function f, which depends on h of t minus 1. There's going to be just an x of t, so I skip f, and just assume now that there is some kind of input at a given time, and I just label that as X, just for simplicity. And then there are some parameters which we are going to fit. So the network will typically be written in a compact way before we unfold it, something like an H. There is an X here, which feeds in. This produces now an output, which I'm going to call for Y. And there is a black box loop here, which now contains this function F. So typically, the way you would write it when you open it up, so when we unfold it, we would have something like dots with previous stages. So I have an H of t minus 1. That feeds in to this function F. I also feed in here this variable X of t. That produces an output H of t. And then this is used to produce, so this is actually, H stands for hidden. So we never see these results. That means that there's something which happened inside this black box, which produces something, and that is used to produce an output Y of t. And then this continues now with a new input of function F that receives a new input X of t plus 1, and it produces an output H of t plus 1, and then it produces an output here, which is Y of t plus 1. And this just proceeds till the final time step. It's normal to actually rewrite this now in the following way. And this is where we're going to stop before we take a break. So we normally skip this function F, and we just replace that with a function H, where we now are going to define this in terms of a hidden layer or a given number of hidden layers. So what happens now is that we have some H0. So this feeds into an H1. Oh, wait, I'm just going to write this a little bit more down so I have more space. So we have an H0 here that feeds in to an H1. And this receives an external probe input, X1. This produces an output, which we're going to call Y1. And that is fed into this loss function, which we're going to call L1. And then there is an external observation at a given time step. So we would have a Y1 observed, like that. This feeds in to the next one, H2 here. And then we have an X2. And this goes up to a Y2, which then feeds into an L1. And then that receives a number to compare with, an observation. And this continues all the way till the final time step. So I'm just going to put dots here and then just write H of n, which is the final step. Now, in here, what we're going to have now are parameters. So these parameters, theta, they are going to be given by matrices, weight matrices, which connect the different inputs and outputs, etc. So I'm going to have a W, a V, there's going to be a bias B, and a bias C. And I'm coming back to how we define this after the break. But we will have a matrix which links the external probe with a hidden layer. So that is a weight matrix, which contains unknown parameters to fit. Then there is a W here, which connects one hidden layer with another hidden layer. And I'm now going to write this with the same symbol. You can, if you want to, you can change the parameters for every stage, or alternatively reuse the weights. So some people also have a mix where you train the weights up to a certain point, and then you use the same weights for the remaining points. So there are many different strategies, and all these are meant to reduce the dimensionality of the problem. Because if you have, let's say, 1,000 time steps or stages, you may have to store matrices at every time step if you want to fit them for every specific time step. So you are going to have a matrix V here. There's a new matrix U. So right now I'm just leaving this unspecified, where I'm changing the weights and biases at every stage or reusing them. The standard approach is to reuse them. So I have a V here, there's my W, and this continues all the way to the final stage. And these are the parameters which we need to fit. And they are normally fit by the backpropagation algorithm. And this is called normally backpropagation in time. So this is the, how to say, the basic layout of a recurrent neural network with the parameters which we need to fit. And then after the break, we are going to look at the forward pass, how that is going to look like. And then we're going to look at the elements which are needed for the backpropagation and the kind of derivatives which we need to add to the calculations in the backpropagation. Yeah.
What is V again?
V is a weight matrix which connects the H1 here with the output.
Well, why wouldn't you pass it W? Because don't you want to know what H1 is passing to H2?
Because this H1 is now fed into an output layer.
Ah, yeah.
So you have a connection between the hidden layers, as you would have with a normal network. And inside here, H1, when you open it up, it can have one single hidden layer, or it can have many.
Yeah.
So this actually produces now an input to the output layer. And this is the Y1 is what your model predicts at a given time step.
Yeah.
Like this sine function, what I did was to train it on the sine function. And then at every stage, every time step, I produce an output from my network. And that's the one I want to compare with an observation. Whether these are vanilla data, like the sine function which you produce, or whether they are real observations. So a typical thing would be if you're doing a medical analysis, you could measure the response of a given patient who has diabetes to some specific stress factors. And then you can measure that response at given time steps. And then you could see if a network could actually make predictions of how a patient with diabetes and one without diabetes would react to a given stress. And that's pretty common. That's a very common application. But time sequences are, I mean, when you do science, I mean, it's something you encounter again and again and again and again. We take a small break, and then during the breaks, we can either just stretch legs, grab a coffee or whatever, but also just discuss the projects and how we want to work, actually. Because I was thinking that I will need roughly a little bit more than the next lecture to wrap up this stuff. And then I thought we could discuss the project and try to team up people and also decide when we want to meet and how we want to work, actually. So I'm just going to put this recording on pause. So a typical recurrent neural network is something now where we have replaced the explicit function which we had for a differential equation now with a neural network. And the forward pass here, when we now have initialized all the weights and the biases, if we look at that one, that is going to contain the following parameters at a given time step or given stage. There's going to be a variable z of t, which is going to be given by this matrix U. And now I'm going to write this in a sloppy way without specifying whether these are matrices or vectors. So U is multiplied with x of t. That's the input at a given time, because that's, as you see here, that connects with this. So it's part of the input to H1. And then there is an input which comes from the previous stage, this one. So that means that there is a plus, a W multiplied with H of t minus 1. And finally, we typically have a bias parameter, this B. And then this is sent in to this function, which we labeled as F, which is now essentially an activation function. It could be a realo, it could be a sigmoid or whatever. And it means that what we have then is a h of t, which is given by this function f, which we have suppressed in a way. And this contains z of t. And remember that these quantities are matrices and vectors. But we use a little bit sloppy notation. So we follow the statisticians because they say you should infer from the context whether this is a matrix or vector or a scalar. And then we have a new variable, which I'm going to call for r of t, which is going to be given by this matrix V. And that takes this output, h of t. So I'm producing this specific function here produces an output. And that output is h of t. And this h of t is now going to be multiplied with this v. And it's going to feed into the output layer at a given stage. And so that means that they have plus, and then they have a bias. So these two parameters which you have here, these ones, these are biases, which in a way hinders that the gradients vanish for us. And then I have a final function y of t, or variable y of t, which is the output, which is now given in terms of this r of t here. So this is essentially what we need to do the feed-forward pass. And then you typically initialize the weights. So there are two common strategies here when you are going to set up a recurrent neural network. And these are as follows. The one is that the weight, we share the weights. Weights are shared, which means that these matrices, U, W, and V, they have the same weights at all stages. The other alternative is that we actually train the weights up to a specific point, or just have weights which are changed at every stage. Change weights at every stage, or every time step. I'm just going to call this for stage. So the network then is going to contain, as we saw here, up here, it's going to contain a set of, actually this should be L2 here. Sorry. It's going to contain a set of functions. So we will have an L, total L, which is now the sum over all these loss functions or cost functions at each stage. So the drawback in computing many of these things now is that we can have gradients when we in the back propagation part, which can actually explode, or they can vanish. And we need to look a little bit more carefully at that. So let me just quickly remind myself of what I wanted to say. Yeah, so the one of the drawbacks here is clearly, if you look at you changing the weights at every stage, is that this is going to require a lot of memory. And this will also complicate the calculations of the gradients when you do the back propagation. So it's normally simplified, this kind of, so this network which you see here is also a network which is highly non-parallelizable. It's extremely sequential. So that means that you actually, if you're thinking of high performance computing, this is a model which simply is not possible to parallelize, because you need the input from a previous time step into the next time step. So it's a model which now contains also long-term memories, because you see now that when what you fit in here is something which will propagate throughout the network till the final stage. So it takes care of what we normally call long-term time dependencies. However, the price you pay is simply with all this connectivity here and all this information which you propagate, is that it becomes inefficient or time-consuming to train. It normally gives very good results, but it's inefficient. So you can look at a less powerful method, where instead of connecting the hidden layers, you actually only connect the outputs with each other. So that's a less powerful method, and sometimes it gives results which are not as good as the one which obviously keeps all these long-term dependencies. But you can actually shorten the network, and a simplification to this. So this is, if we want to summarize, so this basic network here is expensive to train. And it's impossible to parallelize. So one of the ways to reduce this kind of dimensionality is actually only to connect the outputs. So a simpler network, which also is widely used, and it's an option in TensorFlow. So a simpler NN is actually the following. So you would still start, let me just put it down here. So you have an H0. This receives some input X0. It feeds in to H1 here. Actually, this is needed when you're starting the network. It has an X1. There is a connection U here, and there's also an output Y1. And this feeds into this cost function layer. So you would have an L1 here, and you would, squeezing in text here, sorry for that. This is the observation. Now, what you're doing next is that you're not connecting the hidden layers. So we would have an H3 here. We have an X3, an X2 here. And this feeds into a Y2. This is your output, a Y3. And this continues to the final stage. But now what is fed into the network is actually only, so there's a connection here, but it's only this one. So that feeds into H2. And there is a weight matrix here as well, which we need to train. And this one feeds in here. And this one continues feeding in like this. So there is going to be a weight matrix, but this is a network which then has the benefit that it can be parallelized. You can run the calculations at each time step separately. And however, what happens then is that you lose some of these long-term dependencies, unfortunately. Now, when you now are training the network, the standard way is actually to perform a back propagation in time. So if we go back to the previous network, but also this one, previous and this, training goes through the back propagation through time. Is done by what is called back propagation. Through time. And you will see that with the acronym BPTT. So what we need now is actually to train different types of gradients. And what I was going to do then is actually to switch back to the slides. And I have borrowed from a textbook which I actually recommend quite a lot to you if you're interested. So if you scroll down a little bit in the slides here. So here is a general discussions of what we have gone through. So a typical recurrent neural network, when we open it up, it looks like this. You can make it with a simple layer, or you can have a multi-layer. This could be convolution neural networks. It could just be standard feed-forward neural network. So you would actually have to do a training inside the network itself. And that means that you will also, you would typically, when you look at the derivatives and the cost function you compare with, it means that you also need to evaluate the parameters here so it reproduces the output at a given time stage. So this would be a typical setup of the recurrent neural network. So the standard recipe, which is normally used here, is that you would have then an input from 2 points. So you have this one from the previous layer, and then you have the input from the external probe. So actually this is taken from you can see the textbook here. There's a textbook by Sebastian Raschka, who was one of the first people actually who wrote textbooks on Python and machine learning. And it has many nice figures. So this is actually a pretty good textbook if you're interested. And I actually borrow these ones because sometimes it's boring to make figures. And I hope you don't mind. And in this case here, you have also many ways by which you can connect the inputs to the outputs. And there are tons of different architectures here. So if you now look at the back propagation in time, as I said, what you need to do now, and here the notation is a little bit different from the one I used. I used V, W, and U here. But here it has a subscript HX and the HH here. And then there is a similar parameter, set of parameters here. So when you do the back propagation, what you need now is as you see here, is the input to this one, as we discussed earlier. So you have a bias, and you have an activation function here. So when you're training, for instance, the parameters VHH, just to give you an example of one type of parameters, then you need the derivatives for these parameters. If you now look at the derivatives here, you would have the cost function, which is the sum of all the individual elements. And the cost function then will clearly depend both on these parameter sets, which link the hidden layers with the output layer at each stage. And you need then, with the back propagation through time, you need now to set up the derivative for one of these given cost functions as a function of this WHH, which is one of the set of parameters. And you need derivatives with respect to this H of X and Y of H. So there are several gradients which you need to set up. And typically this is done by back propagation and a chain rule, which means that you would just repeatedly use a chain rule, where this is now the, if you look at this last term here, this is normally the way it's done. And this mimics very much what you saw in back propagation for a standard feed-forward neural network. It's actually computed as a multiplication of adjacent time steps. So this would be the standard recipe, which is used to train the weights. And you would have to do this for the weights which link the hidden layers, but also the weights which link the input at each time stage with a hidden layer, and the hidden layers with the output layer. So they need also to be trained. So you have a set of weights and biases, which then are computed typically with a back propagation algorithm. And remember, the back propagation is simply an implementation of the chain rule. And if you're using automatic differentiation, that is reverse mode in automatic differentiation. But you see, the thing gets a little bit more complicated compared to a standard neural network, because in the standard neural network, what we would be doing then would simply be to fit the parameters in one layer. So now you have to go through time here. But technically, it's the back propagation algorithm. So at each stage, you have an implementation of the back propagation algorithm. But clearly, it becomes time consuming if you make this one, if you go back to the figure here, if you make this model more complicated and have many hidden layers, which is also the case in many of these models. Any questions so far? So one of the problems which we face when we are dealing with this type of calculations is that of either vanishing gradients or exploding gradients. So vanishing gradients is something which is also difficult to assess, but you can often change or initialize the weights and the biases so that the gradients don't vanish. The problem, however, the more serious problem here is that of so-called exploding gradients. So let's go back to the whiteboard here and take a look at that specific problem, because that's something which we need to think of. And normally that is done by an algorithm which is called gradient clipping, which is not very satisfactory actually, but that's the standard recipe which is being used. So one of the problems which we face when we look at these gradients, so let me just remind you of some of the expressions which we are looking at. So in the training, we need the gradients. And one of the gradients which we have is the gradient of the cost function at a given stage in terms of the parameters W. And this is given by d of L when we're just using the chain rule of d of y of t. And then we have dy of t of dh of t. And this is then multiplied with a sum for k equal 1 up to n. And we have a term dh of t, dh of k, and dh of k with respect to this matrix W here, or the parameter, these weights here. And this term here, if you look at this one, this is normally calculated as follows. So that shouldn't be. So this term dh of t of dh of k, the standard way by which it's calculated is by this formula here, k plus 1 of n of dh of I with dh of I minus 1. That's the standard formula which is being used. And this formula which you see here is a product of all these derivatives. And you can see now that this can lead, since it's a product, this can lead to two main issues. One, vanishing gradients. And the other one is actually exploding gradients. So both of them are tricky to deal with. Often the vanishing gradients are, cured by looking at the initializations, which guarantees that the gradients will never vanish. So that means you also need to take into account a bias, which doesn't disappear. So often what people do then, if the weights tend to become very small, then they tend to increase the value of the bias. So let's look at the problem with exploding gradients, which is a little bit more serious than the vanishing ones. Actually, both are equally serious. But let's now try to analyze it. And in the analysis here, I'm going to skip the dependence on x. So skip x of t in the analysis. So I'm simply going to assume now that h of t is given by a weight function which connects the new hidden layer at the given time step t with the one at the time step t minus 1. So I've skipped this dependence on x of t multiplied with that matrix, just to perform the analysis here. So if you now look at this one, what you could assume now, if we now use this weight reuse, so weights are normally reused, So you could now think of this h of t as being given by w multiplied with w up to t times. And this is multiplied with an h of 0. And you would rewrite this one in terms of w to the power of t multiplied with h0. So when I have a superscript now, this is the to the power of something. The subscript, it means a specific time step or time or stage. So what we could do next now is that we assume now that this matrix W is diagonalizable. W is diagonalizable. And in that case, we can rewrite this W in terms of a unitary transformation, multiply with a diagonal matrix times U of T. And we know that these are orthogonal transformations. So that means that U of T, they are equal to the identity matrix. So what we do now is to expand, since we have a basis, we expand H0 in the eigenvectors of this matrix W. Vectors of W, and we call these eigenvectors Wi, with eigenvalues which we simply label as lambda y. So that means I'm going to expand H of 0 in terms of these vectors, lambda y, and suppose we have m such states. So we're assuming that W is a matrix. It can be complex of dimensionality m times n. And then we have, well, let's start from 0 to n minus 1. And then we have Wi here. And then we know that when W acts on Wi, that is the same as lambda y Wi. Okay? So this is a standard trick. And it's actually the same trick you would actually use in a Markov chain when you're trying to understand what the Markov chain converges to after a given number of iterations. And in that case, W has to be a stochastic matrix whose largest eigenvalue is equal to 1. So what happens then when we apply W, sorry, not W0, but W on H0, that gives us simply lambda I multiplied with alpha y times Wi. That sounds reasonable, right? Because we have used this equation here, where we simply have assumed now that these are the eigenvectors and eigenvalues of W. So that means that when I apply this many times, when I take Wt times H0, which is now equal to H of T, that becomes simply I of lambda y to the power of T. So this should be an alpha I times Wi here. So we can also assume now that this matrix has been reordered so that we have a descending series of eigenvalues. So lambda 0 is larger than lambda 1, larger than lambda 2, etc., till lambda n minus 1. That means clearly that this will be dominated by when T goes to infinity or becomes very large, then this Wt times H0 is going to be proportional to lambda 0 to the power of T multiplied with alpha 0 times W0. And then you see clearly that if lambda 0 is larger than 1, then this product, which we are, because we are now performing a multiplication by stage. So let me just bring you back the network which we have. So every time here, go back to the previous figure here, every time now we are multiplying W with an H, and we repeat that one many times. And you see now that if this is repeated many times, then the risk which we face is that of a gradient which is going to explode because this quantity explodes. So if lambda is larger than 1, lambda 0, then we can risk of exploding gradients. If this W is a stochastic matrix, then there is no problem because the largest eigenvalue is 1, and then the gradients won't explode. And if we have lambda 0 less than 1, since we have ordered the series of eigenvalues this way, then there's a risk of vanishing gradients. So this is typically a problem which is not that serious in a standard feed-forward neural network because we do it only at one stage. Whereas now we are just reusing the weights And this means that we can actually risk that the gradients can explode or vanish. So the standard recipe for getting rid of that is the so-called gradient clipping or exploding gradients. So if we go to that one, and this is very ad hoc. So that leads to a trick which is often implemented, which is called gradient clipping. So if we just label the gradient, let's just call that as a vector, gradient G. What happens then is that the recipe here is simply that if the norm of this gradient, the norm 2, is larger than a specific preset value epsilon, which you have defined, then we change the value of the gradient by simply taking this epsilon and we divide it by the norm and multiply with the gradient. So this is actually very, very, very ad hoc here. So if we now want to summarize a little bit about recurrent neural networks, so we discussed two basic ways of setting it up. The kind of approach which we also can use are actually different approaches, and one of these is normally called long short-term memory, which we are coming to. But if you look at what we have now, in contrast to a fully a feed-forward neural network, the RNNs, they get new inputs all the time, and the weights need to be updated unless you use the same weights again and again. The challenge which we have is to learn the long range dependencies, the long time dependencies. And the reason for that is that often we want to know this long time dependence. Because if you want to make a prediction, so you train your network within a given time, and then you would like to use this trained model for making predictions of at times far away from what you have trained it to. So clearly, if you have harmonic oscillations or things like that, then your network is going to do an excellent job. If you don't have that and something happens, then you would actually need this long range time dependencies or long range dependencies. So depending on the type of problem you have, you need to think carefully on what kind of dependencies you are sensitive to. So in physics, if you often have forces which have an infinitely long range, then that can actually lead to kind of long time dependencies as well. So in order to train them, you need to keep the internal values in memory until you get the back-propagated gradients. So if you look at the network itself here, if you look at the values which you have, the values you need to keep track of, let me just put it up here. These specific values which you have here, you need the weights and also the biases. And you will also need some of these other parameters, these H of T's, in order to train the network. And that means that you need to store these. So compared with a standard feed-forward neural network, now you have additional memory requirements. And that clearly makes these calculations much more time-consuming than a standard feed-forward neural network with the same number of nodes and hidden layers. So solutions which are often used is to actually stop the training at some point and then keep the same weights and biases throughout the rest of the calculation. Or if you just reuse the weights, then there is no problem. So this normally reduces memory requirements, and it gives also faster parameters updates. The disadvantage is that it's not always able to capture longer dependencies or long-range dependencies than those which you have in this truncated length where you keep the memory. So ways to improve upon what we have here is something which is normally called the long short-term memory. And they're also so-called gated recurrent networks, which we're going to mention a little bit here. So but before we do that, I thought we could just take a small break, if that's okay. And then we just stretch legs again. And we come back and we look at this long short-term memory stuff. And after that, I thought we could just jump into discussions of the project. If that's okay with everybody. Okay, I'm going to. So there are tons of different implementations of these recurrent neural networks. So the one which we have looked at is the one which is really CPU greedy and memory greedy. It does a pretty good job, but then there is actually there are actually other ways by which we can learn an RNN, and one of these is actually what's called a long short-term memory. They normally make the RNN out of smaller modules that are designed to remember values for a long time. So I just wanted to go quickly through some of the images here, and then if you wish to look a little bit later at the details, I mean, you can take a look in both Goodfellow's book and in some of these other textbooks which I refer to. And this long short-term memory is the one which is more used, and it was introduced back in the end of the 90s. And it's a way by which you avoid the kind of vanishing gradient problem. You still have the problem with exploding gradients. And it solved the problem of getting an RNN to remember things for a long time, like hundreds of time steps. And what they did was actually to design memory cells using logistic and linear units with multiplicative interactions. Information gets into the cell, whenever it's a write gate is on, and information stays in the cell so long as it keeps its gate on. And information can be read from the cell by turning on its so-called read gate. And here is, I borrowed heavily from the slides of Sebastian Raschka here. And typically what you would have now in the feed in this network here is that you would have a typical cell which you would define. So this is the input which comes in from the previous one. And here you have the information which comes in from the external probe which you have. And then you have a function here which modulates your results. And this is the one which now produces the final output up here. And this kind of information which you see here, this will be the kind of weights and biases which we have. And this is a kind of information which it keeps, but it doesn't keep it for every cell. So it just keeps for some specific cells. And that's a weight by, so instead of you keeping the information for all the stages, it takes information from specific cells. And the way this is done, if you think of a multi-layer network, what you see now is actually this stage here, where you actually keep track of the information so that you try to, in a way, encode the time information, which then can be reused for later stages. So I don't know how much this actually tells us. So you would have a cell state at the previous time step, which is this one. And then you have the cell state at the current time step. And often the kind of functions which are used to modulate the data are the tanh or just a sigmoid function. These are the standard functions which are being used. And all this information about the weights and the biases is being kept. And you would have an activation from the previous time step, which is fed in here. And then you would have an activation here, which comes from the next time step. So you keep this kind of structure, which you had before. So if we go a little bit back again in time and look at the standard setup of a recurrent neural network, what we had in the previous case is that the long range time dependencies or just the long range dependencies were kept track of by training these weights and biases, which is memory intensive. But what you can do now is that you just keep track of all the information for some specific cells. So every step here can now be replaced by a given cell, or you would just have cells at different positions. And these cells are those where you train the weights and the biases, and you store that information. So that's the kind of difference between the kind of approach which we did here and the one where you try to have this long short-term memory. And the cells then, all this information is actually kept through the training. So you need to store this information. And in here, you have the standard operations, which you've seen before. And often these functions which you use are now standard logistic sigmoid function and a tanh function. And then this produces an output to the next layer. And there's also something which is called a forget gate, controls which information is remembered and which is forgotten. And that can reset the cell state. Basically, these operations, F here, would then contain the output from these different functions which you see here. And then you would have a so-called input gate and an input node here. And again, as I said, the information which you want to use is the one which would be stored in these weights and biases at a given time stage. Oops, there's a figure which is missing here. But anyway, this becomes a technicality, but if you now want to use this, I had made a problem here actually with some images. I have to load them up again. But these are just iterations of what you saw. So the whole thing is that you have specific stages where you now store the information with its time dependence. And the hope is that by storing only specific time dependencies, is that this can be used to keep some kind of long range information about the system.
Typical things like if it's a periodic thing, would it typically then kind of store the periodic?
So you could typically keep, if you have 100 time steps, you could keep every 10.
Yeah,
that could be a typical type of information which you would keep.
Yeah.
But you would have to play around with how much you keep and how much you do not keep. That becomes again a type of hyperparameter which you plug in.
Yeah. Well, are there models where this is you train a thing to learn which ones you should keep and which ones you should?
I haven't looked into that actually, so I wouldn't be able to.
Okay.
So I normally
could infer something about if it's periodic or like these things.
This is things which I haven't explored because I haven't worked so much. The only thing which I've been using. That's the. So this could actually be something which is interesting to explore in the project as well.
Yeah, I think so.
Yeah, no, that could be interesting to explore. And I think TensorFlow has this kind of flexibility. And you can see now that when you want to use these, here there's an extrapolation example in the slides. And these are based on calculations of a many-body problem where I calculate the eigenvalues of a system. And as a function of the number of degrees of freedom, and then I want to extrapolate to an infinite number of degrees of freedom. So I use a training here, and I use a recurrent neural network to actually make an extrapolation. So you can use them. You can use all these methods for extrapolations. So now time in my case is actually a calculation which is done with a certain number of degrees of freedom at each stage. And then I simply use a recurrent neural network to make a fit to the data and then extrapolate beyond the data which I have fitted. So that's one possible usage. And in this case, if you want to use the long short-term memory, you will simply have this LSTM here. So my training data is actually eigenvalues, which have been trained up to a specific number of, this is a quantum mechanical problem where I actually trained it with a truncated Hilbert space up to a certain level. And then I extrapolate to an infinite Hilbert space. But that's not so important. So you can think of just using this as training data and then extrapolate beyond that training data. And you would have to format the data. I don't know how much I should go into details here, but the network in this specific case would then be simply given by the simple RNN. You define the number of hidden neurons, the kind of input you want to plug in, the dense type of neural network, the model which you have, and then I compile the loss function, which is the mean squared error. And then I plug in an optimizer here. But you can then train it with an LSTM. So these are just specific data sets. But I think I have an LSTM somewhere here. Or maybe I made an error here. So I just have to remind myself where I plugged in the LSTM here. Suddenly I've forgotten where I actually plugged it in. Yeah, it was here actually. So in this case, I mean, if you're using an LSTM, in this particular case, what I did was simply just to use this default value with a given number of hidden neurons. I have a 250, and I have only one hidden layer in this specific case. And if you use this LSTM option, that simply bakes in this long short-term memory application. And in this case, I have an activation function, which is a tanh. And again, the mean squared error and optimizes Adam here. So let me just run one of these calculations here. So this is a simple recurrent. Oops, I have to go back. Yeah. And I have. Yeah, I have to go. I forgot to go really back here. So you can see the loss function when you are performing the training, and the loss function is getting smaller and smaller. But in general, it stays around from 10 to the -3 to 10 to the -4. And in my case here, the prediction which I make, when I make the prediction here, so this is just the value of the loss function, but then I have the data. So I actually have the true data, which is the blue line, and then I make the training on the orange, in the orange area. So I actually train up to this point here, and the rest is a prediction. So I use a recurrent neural network because I have equally spaced points here. And I use a recurrent neural network just to make a prediction on data, which doesn't have anything to do with a time sequence, but is a sequence in terms of the number of degrees of freedom in a quantum mechanical system. Yeah.
You know why the loss function was oscillating that?
Yeah, this is as a function number of epochs, you see. So I'm just trying it out as a function of epochs, so it stabilizes after a given number of epochs. So if I have less epochs, it will fluctuate a little bit. And then you can try the with more layers. So in this case, I actually have 2 hidden layers inside each stage. And that often gives a slightly better loss function, but it requires a little bit more time to train. And you see also the number of parameters which you get, actually quite many. So you're getting close to 7,500 parameters to train. So which is quite a lot. But still, it's not that slow. Also because we have lots of data. And in this case here, what you see now is that the prediction is not that good. So you the way you model this depends obviously on the number of layers you have, and you can actually make an overfit if you want to, or underfit. So it's not given that increasing the number of hidden layers actually gives a better prediction. So that's the kind of wisdom which we should always keep when we run these calculations. Yeah, it's I just brought this up because it's it's useful to keep in mind that you might think that the denser I make my network, the better it trains. And this was the case with the LSTM, and I think the LSTM gave a decent result, but actually the best result was obtained with a recurrent neural network with just one hidden layer for this specific case. So the true values, which are the ones you want to reproduce, which are also more time consuming to calculate, actually not that well predicted with the LSTM here. So it doesn't need to mean that a more complicated one gives you a better result. So just keep that in mind. So these examples are more meant as examples when you now are going to dive into the projects. And if you're solving differential equations, I actually haven't done that part myself. So I don't know how a recurrent neural network works on these differential equations. And that would be interesting to see if somebody wants to venture into that. So this is going to, in a way, conclude the lecture part on convolutional neural networks and recurrent neural networks. And then I thought that we could use the rest of the time to actually discuss the projects which we have. And I see that we also have people online here.